Thanks very much. So I wrote something on the board for later, but please, if you can, try and not be too distracted by it until I come to it. So this is based on work in progress with Thomas Dumitrescu and Ken Intriligator. And okay, so I'll start with some general motivation. So the general motivation, this is going to be a talk about CFTs. So why do we care? Well, everyone knows that CFTs are a good starting point for understanding general field theories. So why is that? It's because Wilson taught us a long time ago that if you have UV complete quantum field theory, you could think of it as an RG flow. In the infrared, you have some IR CFT. And in the ultraviolet, if your theory is UV complete, in the context of quantum field theory specifically, you'll have some UV CFT. Now, why are CFTs interesting then? Is because they're more constraining. So, at the endpoints of this flow, the symmetry enhances from the Poincare group to the conformal group. And this enhancement of symmetry has many consequences, which enable us to say more about the endpoints of the flow than we can say about the generic field theory in the middle. Okay, so in discussing RG flows today, it will be important to distinguish two kinds of flows. These are flows. You should think of flows as breakings of conformal invariants. So the two types of breakings are spontaneous versus explicit. So let's focus on this case first. So in the spontaneously broken case, we can say something because of Goldstone's theorem. So here, we know that the low energy theory contains some scalar field, which is called the dilaton. And this guy here is the Goldstone boson. For breaking scale invariance. So in the spontaneously broken case, you can understand a lot about your flow by examining the effective action for this scalar field sigma. To leading order in derivatives is, of course, a free scalar by Goldstone's theorem. But at higher order in derivatives, the effective action for sigma encodes things like the A anomaly, the difference between AUV and AIR. Okay. Spontaneous breaking, we know lots of examples in supersymmetric field theory. If you take some CFT and you put it on its moduli space away from the origin, that's, of course, a spontaneously broken conformal invariance. Okay. Now, today, instead, I'm going to focus more on explicit breaking. So in the explicit case, we'll be able to say a lot today because explicit breaking is triggered by operators. By that I mean we're going to take our action and we're going to deform it as follows. So what are the symbols here? This O here is some local operator. And delta is its scaling dimension. This mu here is some reference scale. And this whole thing together has total correct dimension 0. And then this is some coupling constant, which is dimensionless. Okay, so this is what we mean by an explicit deformation. So examples of this are, of course, mass operators and various other familiar types of interactions. So as we know, we can broadly split explicit deformations into 3 classes. So the 3 cases. Okay, so the cases are just determined by the sign of this exponent here. So we look under RG flows. So under an RG flow, lambda will scale, so if I scale mu to epsilon mu, where epsilon is less than 1, and I want the physics to say the same, then I should scale lambda to lambda epsilon to the delta minus d. And so then the 3 cases are irrelevant. So that's when delta is greater than d. And in that case, lambda goes to 0 as you go to the infrared. Okay. Then there's relevant. That's the opposite. In this case, lambda goes to infinity in the IR. This is like a mass. And then there's marginal. That's delta equals d. And then you can't say, just from looking at the, to first order in the RG flow, the theory preserves conformal invariance. This deformation preserves conformal invariance. But you have to look at higher order corrections to really know what happens. It can go into this camp or this camp. So then you split this guy into further 3 other cases by looking at higher order corrections, log corrections to the RG flow. And you get marginally irrelevant, marginally relevant, and finally exactly marginal. So of course, this case, the log corrections push you to this side. This case, the log corrections push you to this side. And this case, you stay exactly in the conformal world. So these are interesting. These are like coupling constants. Okay, so all this is very basic and kind of a review. Now, if you don't give your theory any more structure, then you can't say much more than what I've put on the board here. But if you give your theory some supersymmetry, and you ask that your RG flow preserve that supersymmetry, then you can say a lot. So let's add supersymmetry. So from now on, I'll discuss superconformal field theories, and I'll assume I'm going to study flows and marginal deformations. That preserve all supersymmetries. So from now on, I just won't specify that that's what I'm studying. Okay, and then you can say a lot. So let me tell you some results that you get. So let's make a little table. So this will be the space-time dimension. This will be relevant deformations. This will be marginal. And we can ask in each case when they exist and when they don't. So in dimension 6, I'll show you that there are no relevant deformations and there are no marginal deformations. In dimension 5, there are no marginal deformations, but there are relevant deformations. In dimension 4, okay, so these two cases I didn't have to specify how much supersymmetry I was talking about. This is true just for the minimal supersymmetry case. In dimension 4, I have to tell you how much supersymmetry. So to get interesting results, we'll put n equals 2. In that case, both exist, but I'll come back to this case. And then in 3D, let me put n equals 3 to get interesting results. In that case, there exists relevant, but no marginal. Okay, so in all of these cases, we don't just have an existence theorem, we have a kind of detailed understanding of what the deformations are. And they are no surprises. So in this case, we can say that relevant deformations are in one-to-one correspondence with flavor symmetries. So for each U1 flavor symmetry of your theory, you get a relevant deformation. We can also say a little bit in this case. So this here I was just saying marginal, but I didn't tell you whether it was marginally irrelevant, marginally relevant, or exactly marginal. And here you can prove a little theorem that says that these are all exactly marginal. So in other words, in 4D n equals 2, marginal implies exactly marginal. Okay, so these are the results. So for most of the rest of the talk, I'll try and explain how to do this. Are there any questions so far? No?
You are going to also explain the six-dimensional cases.
Yeah. No, I mean, I can't explain sort of all the cases in the talk. I'll probably just explain in detail how to do this case.
Is 4-dimensional n equal 1, 2 loosely constrained?
So in 4-dimensional n equals 1, you have both. And, well, you can still say something. I mean, you can say what kind of multiplets. In fact, Seiberg, Tachikawa, Komogorski, Wecht, and Green, thank you, did indeed say what kind of multiplets marginal and relevant operators are in the 4D n equals 1 and 3D n equals 2 cases. And in those situations, you have both. And it's not true that marginal implies exactly marginal. So, okay. With more than 4 supercharges, suddenly you can put a huge constraint on everything. Okay, so how are we going to do this? So what's the method? So say, this can all be phrased without an action, but let me just phrase it with an action so that it's very concrete. Say S naught is the original action. And Q naught is the original supersymmetry. Okay, so now we deform this. And to first order in our deformation parameter, S naught will change to S naught plus S1, where that thing is right there is S1. And also the supersymmetry would change. So these guys here you should think of as first order in the deformation parameter. Now, what does it mean for the deformation to preserve supersymmetry it means that the total new supercharge annihilates the total new action. So using the fact that Q naught annihilates S naught, I get what appears to be the first order constraint that 0 is equal to Q naught S1 plus Q1 S naught. So far I haven't told you anything about Q1. I've only told you about S1. But I claim that this term here is actually secretly higher order. So why is that? Well, it's because Q1 acting on S naught is some variation of the action. And so if I didn't have S1, this thing would vanish on shell. Therefore, in addition to the ordered lambda term that's in Q1, you get an ordered lambda term because of the equations of motion appearing here. So to leading order in the deformation parameter, we don't need to consider this. The leading ordered piece is just this. Okay, now it becomes very straightforward, because this is a question about the old supersymmetry in the theory that we started with, and this S1, which is phrased in terms of operators in the theory that we started with. So we need Q naught S1 is 0. So I just erased what S1 was. This thing here was the proportional to the integral of this. So we need Q naught acting on O delta of x is 0 up to total derivatives. For all supersymmetries. So that's what we need. Okay, well, we can classify that. The reason we can classify it is because in superconformal field theories, local operators are in representations of the superconformal algebra. Since they're in representation, and these representations have, in particular, all been worked out. So we can just look at the list and see what's possible. So now let's do that. Questions about this argument? No?
About this expansion order by order. So what if you work with the off-shell supersymmetry, then there's no variation of the supersymmetry?
Then there's no variation of the supersymmetry at all. No, but I mean, like, the variation of F contains W, for example, right? Like, W appears.
That's on shell.
The equations of motion set F equal to W on shell, right? But
the transformation is independent of the action.
well, I phrase it this way because really I just want to get to a problem in the original action, with the original operators. Maybe for theories where you could phrase everything off shell, there's something even simpler to do.
I mean, you will still get this equation, just a further order.
Yeah. Okay, so local operators are in reps of the superconformal algebra. Okay, so on the board, I won't do all of this, but I'll talk about the 60 case. Okay, so the example I'll give will be t equals 6. So here I'm going to talk about the minimal superconformal theory in d equals 6. So the superconformal group is OSP 8/2. And this contains inside it bosonic subalgebra that I'll use, which is SO2, whose eigenvalue is the scaling dimension delta, Lorentz representation. I'll come back to how I label this guy, and an SU2, which is an R symmetry. Okay, well, maybe I'll put this over here. So local operators will be labeled by their quantum numbers under this group. And what are the quantum numbers? So there's delta, which is the scaling dimension. There's M1, M2, and M3. These are, sorry, this should be SO6. So here I'm going to use the fact that SO6 is locally isomorphic to SU4 and label representations by Young diagrams, where the first row has length M1, the second row has length M2, and the third row has length M3. You know, some familiar, let me put a parentheses here, some familiar representations. So this guy is the spinner. This is the spinner bar. This is the vector. This is the energy momentum tensor. This is a self-dual 3 form, and so on. Okay, so Mi is length of ith row. Finally, the convention I'll use for SU2 is that, let's see, what is my convention? So they'll label them by a representation, by an integer r, little r rather, where dimension of rep is r plus 1. Okay, so this is my list of conventions. Okay, and then local operators. Well, let's leave the results actually. So local operators are in multiplets acted on by Q. And one thinks of these as raising operators. At the bottom is a primary. And it's customary to label the representations by the quantum numbers of the primary. Okay, so luckily for us, someone else has worked out what they are, and now we come to this table. So this was worked out, well, part of it was worked out by Minwala. And then it was really nailed down by Dobrev. Okay, so there are all these 11 distinct kinds of representations. And so the L representation is the generic one. That has the feature that it's not annihilated by any supercharges. And then these remaining 10 guys, which have a subscript, are short in some sense. And the way in which they're short, I haven't exactly specified here, but so this Rn has a null state at level n. So that means you have to act with n q's and do some projection in order to get 0, acting on the primary. So you can also say exactly what that projection is. It's all worked out. I just didn't want to write it on that table. So, for example, say the C1 type operator. How do we read this table? Well, C1 has M2 and M3 0, but not, in general non-zero M1. Actually, it's supposed to have never 0 M1. So the primary is a guy like this, where here the i's are SU2R spinor indices. And the alphas are SU4 spinners. And this guy, because this is C1, it has a null state at level 1. What is that null state? Well, I didn't write it there, but one can work out. So the Q's are spinners under both SU2R and SU4. And if you really work out that classification, you see that the following thing is 0. So you symmetrize on all the R symmetry indices, and then you take the Lorentz symmetry indices and you project it onto this representation. So this is 0, that projection. So all these short guys have some kind of thing like that.
This E4 guy in 6 dimensions is just a scalar. Let's say we take R equal to 0. It's a
Yeah.
scalar with 0 R symmetry and no other charges. And that's a short representation?
Yeah, there is such a short representation.
But that's due to the scalar in ADS7, no? The free massless scalar in ADS7.
No, the free mass.
Because it's dimension 6. What is the null vector?
This guy, you take 4 Qs and you act on it with 4 Qs. You symmetrize all the R symmetry indices and you anti-symmetrize all the spinor indices. Okay, let me take actually this moment to give some examples of things on this list. That you can cook up very quickly. Okay, so for example, the free hyper. This has M1, well, let me put a column here. M1, M2, M3, R delta. So the free hyper has this set of numbers equal to 0, 0, 0, 1, 2. And this is a D1. The free tensor has 0, 0, 0, 0, 2. And this is a C2. A conserved current has 0, 0, 0, 2, 4. This is D1 again. The energy momentum tensor has 0, 0, 0, 0, 4. Clearly, I'm not very creative since I only come up with scalars. This is B3. Okay, I'll come up with something non-scalar right now. Let's. So it's labeled by the bottom component. So what this says is that the bottom component of both of these multiplets is a scalar. So in order to get the conserved current, you have to go up with 2 Qs. That's because if you start with the trivial representation, you hit it with 2 boxes, you can get to the vector. And to get to the energy momentum tensor, you have to go up with 4 Qs. So that's because that guy has 4 boxes. There's a higher spin current. So this kind of thing, phi I bar, dA1, dAm, phi I, minus traces that I won't write. This has where this phi is a free field, free hypermultiplet, say. M0, 0, m plus 4. And this thing is a B1. Okay, so there's some examples from free fields and familiar multiplets. Okay, now you have this list, you just proceed. There's, it's pretty clear what we're supposed to do. We need operators that are of dimension less than 6, or less than or equal to 6, and that are annihilated up to total derivatives by all the supercharges. So we have all the representations, we just go through and we check. Okay, that's very tedious, so I won't do it all on the board. Let me do one example so you see what's involved. Let's go back to this C1 guy. Okay, so we want, if we take the deformation of the Lagrangian, delta L, we want this to be less than or equal to 6, and we want delta L as a Lorentz singlet. This guy was labeled by 2 quantum numbers, R and M. That M was M1. And this constraint already restrict you to 3 cases. You see there's an inequality on the dimension, so I can't consider general R and M. There's an equality on the dimension. If I consider too big of R and M, I'll clearly already get out of this situation. So there's just a finite number of things to check. So, this one, say. The candidate deformation.
Sorry. And you allow yourself to look for the scalar at any position in the multiplet?
Yeah. I mean, it has to be annihilated by all Qs, so that's very restrictive.
Can it be A? It has to be the top.
Yeah. Okay, so what would you write in this case? Okay, so this guy here in the case 1,1 is just a guy with 1 spinor index and 1 R symmetry index. To make a Lorentz scalar, we have to act on him with 3 Qs. I need more space. Back this up. And then there's an invariant tensor. So this is your candidate variation. The delta, the scaling dimension of this thing is C1. So this thing has, this should be a half here. Sorry, this should, that should have been a half. Okay, so this thing has R is 1. So that gives me 2 plus 2 is 4 plus a half. And then plus 3 halves, so this gives 6. Okay, so what's wrong with this? Well, I know over here that if I symmetrize on, say, J1 and I get a total derivative, or 0, because that's what the null state was. So that means that this thing should be antisymmetric in order to be non-zero. It needs to be antisymmetric on I, J1, J2, and J3. But that's just not possible because there are too few indices. These only run over 2 values. So okay, so that shows that for this particular kind of representation with these particular quantum numbers, you can't actually get a deformation. Okay, so it's very tedious to go through this whole list, but you can do it. And there are various different failure modes. This is one kind of failure mode, and there are other kinds of failure modes that prevent it from working. Actually, I guess we can erase the table now.
Only 4 greater than the dimension of the lowest guy is the D's. And that already only offers you one option, which is R equals 1. So isn't there only one thing to check?
The only multiplet that, can you say your...
The thing, because only the top component of the multiplet that you get by acting with Q's can be the deformation. You can just ask what's the difference between the dimension of the top component and the dimension of the bottom component. And for a D multiplet, the answer is 4. For everything else, the answer is greater than 4. If the answer is greater than 4, then you can already cross out all the other guys, because all of the dimensions of the primaries of all of the other guys are greater than 2, or greater than or equal to 2.
The gap is not 4, it's 2. There are 4 Qs.
But,
Because I construct the multiple with 4 Qs, not 8 Qs. That's one. Yes, what? The
Something that
No, but sorry.
I mean, there is a simplification. I mean, you don't have to do literally each case by case, but I just wanted to show the most pedestrian thing. No, that's fine. Okay. Good. So let me... Okay, let me give you some organizing intuition for why you could expect such a result, actually. So let's consider a hypothetical situation. Suppose you have a CFT, with an exactly marginal deformation. This will be intuition for why the exactly marginal guys don't exist. And suppose further that this deformation breaks a flavor symmetry. Okay, not all exactly marginal deformations are like that, but let's just consider this for the sake of argument. Well, what should happen? So let's call lambda the parameter. And let's say lambda equals 0 is our original CFT. So at the CFT and lambda equals 0, we know that the current has dimension equal to d minus 1. The integral over space of one of the components is supposed to be a charge, which is dimensionless. At the CFT where we turn on this parameter, but we keep it small, J should move up. If it has this dimension, it's conserved. So it has dimension d minus 1 plus something of order lambda. So this situation, this hypothetical, can only happen if the scaling dimension of J can deform infinitesimally. Well, can deform a little bit. Okay. So now we go over here. Well, I just erased it, actually, this table. But the conserved current in 6 dimensions is in this kind of D representation. And it's separated by a gap of at least 2 from its nearest neighbor. So if you want to have a non-conserved current in 6 dimensions, its dimension must jump astronomically. Just looking at that table that I erased, in 6D, delta of J would be 5 if conserved, but must be greater than 11 if not conserved. It would jump, in other words, if it's not one of these special values, it would jump from a D representation to a general long representation. So that shows that this is just impossible. This just cannot happen. So you can't have any marginal deformations that break flavor symmetry. Okay, you could, of course, wonder if you have marginal deformations that preserve flavor symmetries, but you can check that you don't. And this is actually the case in all. This is the case in all the situations where you can rule out marginal couplings, that there's a kind of gap between the conserved current and the generic representation.
So can you sketch the argument doesn't break flavor symmetry?
If it doesn't break flavor symmetry, you just go through and check, like I was doing before. You can shorten your work using some of the ideas that Chris was saying, but you still have several cases to check. It's a finite list, so it's just a finite amount of work. Yes, so in 4D n equals 1, this happens. So if 4D n equals 1, actually, what happens, that's what I was coming to. In 4D n equals 1, if you have a marginal coupling, you could ask, a marginal operator, you can ask when does it become exactly when is it exactly marginal and when is it marginally relevant or irrelevant? So I'm coming to that, yeah. So in 4D n equals 1, you can have a marginal operator, which can become marginally irrelevant, and it can only become marginally irrelevant if it breaks a flavor symmetry. And the way it works is that in that case, with that amount of supersymmetry, the conserved current multiplet is at the bottom of a continuum, and so it can deform a little bit its scaling dimension. But in 40 n equals 2, actually, you can see that, that the conserved current is still an isolated guy. And so you can use this kind of argument to prove that marginal implies exactly marginal in 40 n equals 2. It's because it's not possible for this guy to pair up with the current multiplet and to get a long dimension, to go into a long representation. Okay, in the last few minutes, well, are there any questions about this? No? Okay, in the last few minutes, I'll instead turn now to a simple physical application. So let's consider the status of super Yang-Mills in 4, 5, and 6 dimensions. Okay. 4D, let's say n equals 2. I'm just talking about pure super Yang-Mills for the moment. Well, we know that this is a UV complete field theory on its own. And you can think of it as an RG flow. In the UV, you have some free non-abelian gauge theory. That's asymptotic freedom. And in the IR, it's in the Coulomb phase, according to Seiberg and Witten. It's some U1 to the n. Okay, so that story we all know very well. What about 5 dimensions? Well, in 5 dimensions, super Yang-Mills is not UV complete on its own. So we can imagine an RG flow where in the IR, we have super Yang. And you could ask, is it possible that in the UV, there's some CFT? And of course, in the 90s, Seiberg and then Seiberg and Trilligator and Morrison and subsequently many other authors said that the answer is definitely yes. So there's some UV CFT. And it flows in the infrared to super Yang-Mills. And this is an explicit breaking of conformal symmetry. And the way it works is there's a mass parameter. So this is a mass parameter. And it's the coefficient of some relevant deformation up here. And we know that that's consistent because we worked out that there are such relevant deformations in 5 dimensions. Finally, let's come to 6 dimensions. So this is such a compelling picture, you could ask, could it happen in 60? Why not? Maybe this could still be a mass parameter. But actually, we've now proven that it's impossible. There's no UV completion in field theory. So why is that? Well, you can give many reasons now. The simplest is just that super Yang-Mills here, it lacks a Goldstone boson. Right? We've proven that there aren't any relevant deformations in 6 dimensions. So the only way to break conformal symmetry is spontaneously. But there's not even a scalar in the Yang-Mills multiplet in 60-1-0 theories. So let's give our reasons. I'm talking about 1-0 right now, yeah. But I mean, more supersymmetry is a special case. Okay, so no Goldstone boson. For spontaneously broken scale invariants. You can actually be more specific. I mean, that objection that there's no scalar, of course, I could just add some free hypers, and you could say, okay, well, maybe those are the Goldstone boson. That's not good enough. You see, 1 over G Yang-Mills squared, if it's there in the infrared, if you have a super Yang-Mills sector, then this should be the coefficient of a relative operator in the UV. So the only way out is that this actually is the VEV of the dilaton. I called that sigma before. So what this little theorem predicts is that in order to have a UV completion in field theory, you have to have interactions of the form sigma f squared. In the low energy action. Now, of course, in practice, these are the types of interactions one finds when you have a tensor multiplet coupling to a Yang-Mills field. So this is a kind of long-winded way of explaining that fact and sort of why it had to occur. Okay, if there are no questions, I guess I'll stop here.